So today we are going to discuss the complex analysis. So in this complex analysis, right, what we are going to deal is, so it's not complex numbers. This is complex functions what we are going to deal with. Now when we are dealing with the functions, obviously the calculus comes into picture, right? So this calculus, now it is a complex calculus what we are going to deal. So the basic functions of calculus are, one is the limits, the second one is continuity, and the third one is the differentiability, so these are the fundamental aspects of calculus. Now these fundamental aspects applied to the complex part, so this is what we call as the complex analysis. Now in this, the way we have done for the real analysis, if there is a function f of x, for that actually we have identified the limit extends to a, f of x actually we found in the way that is limit extends to a plus f of x, we found it, and then this is what we called as the right limit. Similarly, limit extends to a minus, which we call as left limit. Right? So these are the two different limits. Suppose if left limit is equal to right limit, limit extends to a plus f of x is equal to limit extends to a minus f of x is equal, then we say that the limit exists for a real function, correct or not? So this is the condition for the limit to exist for a real function. Suppose if the same value is equal to the function value at that point, that is f of a, then we say that the function is continuous. Right? So this is the background that we need to be understanding before we starting the complex analysis from the real analysis, right? So here there are two different aspects. One is the function left limit and right limit. Both should be equal. And if you want to say the function is continuous, suppose in a short form, to identify whether a function is continuous or not, you can just draw a graph of the function. Suppose if you are able to draw the function without lifting the chalk piece, then we say that the function is continuous, correct or not? Without lifting the chalk piece, if I could able to draw the function, then between these limits where I have followed, I didn't lift the chalk piece anywhere in drawing this entire curve, right? So that's why we call this function as a continuous function. Suppose if I have to lift the chalk piece while drawing the curve, then we say that the function is discontinuous, correct or not? Got it? So, but mathematically how do we express it? Now, if you randomly take one point here, and here if I am approaching from the left side, and then I will be identifying the point function, so I will be identifying the function value at that point before approaching this point. So I am trying to approach, but I have not reached it from the left side. Similarly, from the right side also, you are trying to approach the function value from the right side, but I have not approached it. So you are approaching it, but you have not reached that point. That's point we call as the approaching value of the function. So that is closure but not equal. Left side also closure but not equal. Now these two are equal, then we say that the function value is limit exists at that particular point. So this arrow and this arrow will represent that. Suppose if the function value is also equal, that means if I calculate f of a, then that is coming out to be the same value which is equal to the limit, then we say the function is limit. So for the function it is continuous. The same thing mathematically you can identify without lifting that point chalk piece. If you are able to draw the curve, then we say the function is continuous at that point. Got it? Understood? Do you have any questions on this? Now, based on exactly what we have done here, we will be extending the same thing for the complex analysis now. Just note down this. I am going to extend the same thing for the complex analysis. 10. What do you want me to repeat? See this. Here actually in case of a single independent variable, single dependent variable. So that is for the function y is equal to f of x, you want to identify whether the limit exists for a point limit extending to a or not. For that what you have done? You have identified the left limit, that is a minus. That means suppose this a value is 10, then the left limit we mean 9.9999. So like that actually 9.999 is not equal to 10, but it is almost 10. At that point, we will try to calculate the value of the function which we call as the left limit. Similarly, from the right side, you are trying to approach the value of the function at x is equal to 10, which means the value is 10.000001, but which is not equal to 10. So which means that is almost closer to 10, but not equal to 10. For that value, if you want to identify the function, so that value we call as the limit of the function from the right side. Now in both the cases, if the limit value that is at 9.999 and at 10.0001 both are equal, then we say that the limit value exists. Right? So which essentially means that the limit actually is coming to this point like this, and then suddenly if it is breaking from this point and then shifting to some other location, we say that there might be a discontinuity that exists. Got it or not? So now actually if the function value is exactly equal from the left side and right side, then the limit exists at that particular point. So that means if you are approaching from the left side and right side, there is a possibility that you might be reaching the same value. But exactly at one point, we don't know whether it is reaching the same point or not. So if it is also reaching the same value, we say the function is continuous. But if it is not, then it is the left side and right side limits are equal, hence the limit exists, but it is not continuous. Got it? For any continuous function, you will be able to draw the graph without lifting the chalk piece. So the reason why we are analyzing this is, usually the functions are actually defined this way. F of x is equal to x square if x less than 0, and this is equal to 1 by x if x greater than 0, and this is 2x if x equal to 0. This is how actually usually the functions are defined. So this is usually the behavioral curve. For example, if you take one particular student while entering the class, so before entering the class, his behavior is completely different, and once he enters the class, his behavior will be completely different. But we are trying to model the behavior of the same person. So that's why the function of the same person we are dealing with there, right? So hence, before entering the class, that is left limit. After entering the class, that is the right limit. In both the cases, if he is exhibiting the same value of the function, then we say that for the person, right? So his behavior is more or less same. But while entering the classroom, that is when he crossing the door, right? We don't know what kind of behavior he exhibits, right? So if the value of the function is same there also, that means his behavior, there is no change. While crossing the door also, then it is a continuous function, correct or not? So this is exactly what we are trying to model mathematically. So the behavior of a single person. So that's why while before entering the class, he may be drastically different. After entering the class, he may be gradually slowing down from his original behavior. While entering the class, that is before just crossing the door, he might be exhibiting a different kind of behavior it is, right? All the three different cases we will be analyzing. Suppose if all are same, he is a normal person. If it is not same, then he is a drastically changing behavioral person, right? Got it or not? So if all are same, then that's what we need. That's what we call as the continuity of his behavior. Got it? So mathematically, the way we find out is the left limit, right limit are equal, and it should be equal to the function value also. That is, while crossing the door also, he should be exhibiting the same kind of behavior. Got it? Now actually, the extension of the same thing for the complex analysis, that is the limits. But complex analysis, the main reason why we are extending here it is not like real analysis. So in that, we have only in real analysis single variable function. But here, two different independent variables together we call as a single variable called z. That means we represent the function value w is equal to f of z. As I said earlier, w has to be expressed as u plus iv and f of x plus iy. So here, two different independent variables together are coming as single function, that is w is equal to f of z. Now here, if you wanted to identify any single value, it's not like x, it is both x and y together. So that's why this value is represented on the z plane. So this z plane we mean this is xy plane. So on the xy plane, if you wanted to locate any point like this, for this value we have x1 plus iy1. Similarly, if I identify one more point, x2 plus iy2. So this is how actually each and every point is identified in the complex plane or in the z plane, that is x and y plane. Now this is a complex function. For each point, right, I have to identify the corresponding function value here, right? The corresponding function value is very crucial to understand. Earlier, in case of real valued function, you are trying to identify the point always on the x-axis. Now it is no more on the x-axis. It is both x and y-axis together. That's why it is a point now. It's not a line. Right? So here, when you wanted to identify the set of all the points, earlier when you are trying to say limit x tends to a, that means you are approaching from the left side or you are approaching from the right side. But here, if I say that limit z tends to a like this z is a complex number, a is a complex number. Now this complex number represents a point. This point is not on the x-axis. It is in between x and y somewhere. Maybe here, or maybe here, or maybe here. That means you have to associate both the values together. So this point can be approached from all the different directions like this. So it's not like only left limit and right limit. It may be all the infinite directions together. Got it? You have to approach. Now, the set of all the points for which you wanted to identify will constitute a region like this. Now, within this particular region, you wanted to identify the function value w is equal to f of z. The way you have identified in a real valued function, so that is on the for each value of x within this particular range x1 to x2, what is the function value? So that's what you are trying to calculate. Now this is what we call as the domain, and the function values we call as the range. Now exactly in the similar manner, you cannot define a domain on a single line like real function. The domain is no more a single valued function. It is two different values together. It will constitute a region. Got it? So the domain has to be defined on a region called R. Correspondingly, if the function value you have to represent on the UV plane. So here, for each value, if I substitute in this function, automatically I will get a value of w which is equal to u plus iv. Now this is u plus iv. I can identify one more region which will get the value, set of values depending upon the function value. So for each value, there might be a corresponding value in the other region, which we call as r dash. Got it? So this is how actually you are representing a complex function with two different two-dimensional geometries. One is the z plane, another is the w plane. In the w plane, we have got the r dash as the range, and this r as the region of interest, which we call as domain. Got it? Now, if you wanted to identify the limit of the function the way we have done in case of real analysis, it has to be approached in all the 360 different directions. That means for the existence of the limit for any complex function, you have to check for infinite number of directions, not a single direction or two directions or three directions. Infinite number of directions you have to identify. That's why there is a possibility that you might have identified 3-4 different directions and then we found that everything is proper. But there might be one more direction which you don't know where the condition fails. Hence, we are not very sure whether the function is limit exists or not at that particular point. Got it or not? Earlier, you are comfortably verifying that from the left side and right side together, you are identifying the limit value and you are concluding that if both are equal, the limit exists. But here, there is a possibility that you can identify infinite different directions. Now, each direction has to satisfy the same condition of the limit existency. So whatever may be the direction you will be approaching the point, the limit value has to be same. If at least one direction, if you are able to find out where the limit value is not same, then the functional limit doesn't exist at that particular point. Now, how do you verify? That's why actually the questions are based on this concept. So here the limit exists in certain directions, some standard direction. We don't know, in one particular direction the limit may not exist. That's why as many number of conditions as you are aware, you have to test for the limit existence there. Got it? Understood? So just note down this. I'm going to just define the limit of a complex function. Okay. A function f of z is said to tend to limit L as z approaches a point z0 as z approaches a point z0 if for every real epsilon we can find a positive real delta such that f of z minus f of L modulus less than epsilon for z minus z0 modulus less than delta. That is, for every z not equal to z0 in the delta disk, of z plane, f of z has a value lying in the epsilon disk. Of W plane. Symbolically, limit z tends to z0, f of z is equal to L. So this is the definition of the limit. Now, to understand this from the statement, it is very simple. See this, there is one xy plane which we call as the z plane. Now on this z plane, you are trying to approach limit z tends to z0. That means let us identify a point called z0. Now I am trying to approach that point in all the 360 different directions. That is, I can identify a small disk like this, and this disk we name as delta disk, where the radius of this, that is z minus z0 mod, is less than delta. That means this radius is less than delta of that disk, right? So that means within this region, whatever the point you select it, now the function value, if you correspondingly map it on the W plane, it will be on a different disk like this, and this disk is epsilon. Got it? And both are almost 0. That is the condition there. So you are trying to approach this point, you are trying to approach the value of epsilon, so this value here. So this point is W naught. Got it? So this W naught is the value which we are going to get it when you are approaching the value of Z naught. And this W naught you have defined as the limit L. So that's why limit Z tends to Z naught f of Z is equal to L as long as within this delta disk, which is almost 0 radius, if you are approaching this value Z naught, you will be getting a value of L, which is almost with a 0 radius circle. If you are drawing within that, the value has to be confined. Got it? Which question? So this is just the definition of the limit. In the real analysis, the limit, the way we have defined is left limit and right limit should be equal. But here in complex analysis, there is nothing like left and right. There are infinite directions. Now all the infinite directions, how do you define? You are defining a specific region of delta disk. Delta disk, we mean you are drawing a circle of radius delta, which is almost 0. That means you are trying to approach the value of Z naught from all the 360 different directions together into the value of Z naught. So this region we have defined with a letter called delta, which we call as delta disk. Now if you are approaching that value, the corresponding value W is equal to f of Z, right? The corresponding value of f of Z, if you calculate it, you have got one value called L, and this L value for all the point here, right? For each point there will be an associated value here. So if you identify this point, there will be an associated value here. As long as within this delta circle, if you are able to identify the point and find out the function value, the value, it should be within the region of L with a radius of epsilon, which is almost 0 again. Got it or not? You are trying to limit the values to a confined value. Here delta and there L, that's it. Epsilon disk. Got it? Understood? This is what is the definition of the limit in case of complex analysis. I hope everything understood. So you can note down this definition. Anyway, we are going to deal with the examples. I am going to deal with it. So first you note down this definition. Then we have to calculate it anyway. This is the limit. Now this limit we are learning just because you wanted to find out the derivatives. Now the continuity of the same thing you can define if the same limit Z tends to Z naught, f of Z, if the same value is equal to f of Z naught, then we say that the function is continuous. So this is mathematically. The function is continuous. Coming to the derivative, limit dw by dz is nothing but limit delta z tending to 0 f of z plus delta z minus f of z divided by delta z, and this is the derivative function. Got it? This is the derivative. Here see this dw by dz, the way we have defined normal derivative, limit delta x tending to 0 f of x plus delta x minus f of x divided by delta x. So this is the limit of a normal function, which we define this as dy by dx of f of x, or in general dy by dx. Now exactly the same thing we have done here, but each z represents two different independent variables together, which we call as x plus iy. So that is the complexity here. Now to identify the derivative, the limit has to be exist for this particular function. That is, limit delta z tends to 0 has to exist for the function f of z plus delta z minus f of z divided by delta z. Then only we say that the function derivative exists. If the derivative exists for all the points within a specific region, then we say that the function is analytic within that region. Got it? Now, for that there is some theorem called Cauchy-Riemann equations. These are the necessary and sufficient conditions. Conditions for a complex function derivative to exist. So these are the necessary and sufficient conditions. In short, we call as CR equations. These are the CR equations. Now, these necessary and sufficient conditions we have to identify and prove it. Now here, the way we have defined, right, for this particular function, we have to identify the derivative value, which essentially means that limit delta z tends to 0, f of z plus delta z minus f of z divided by delta z. Now, for the existence of the limit, you will be verifying the left limit and right limit. Exactly in the similar manner, here you will be verifying the left limit, right limit, or the horizontal limit, vertical limit, and slanting limit. Three different limits that usually we identify, because it is very tough to identify all the infinite different directions. So at least you are generalizing the limit value to exist for this particular point in the xy plane. You will be approaching this value along x direction. You will be approaching this point along y direction, and you will be approaching this point along some random direction. So here, all the different directions, we say that this is limit delta x tending to 0, delta y tending to 0, and here y is equal to mx and x tending to 0. This is how actually we do it. Got it? So there are three different directions you are trying to approach it. One is the x direction, y direction, and y is equal to mx direction. So these are the three different directions we usually check to identify, at least at the base level, you know that the limit exists for that particular function. Got it? Okay. So these CR equations, I am going to prove it if you note down the statement. Yeah, like we have done in calculus, left limit and right limit. Here you are doing three different directions. So one is the variable direction, y is equal to mx, where m is a variable. So for all values of m, the value has to be same, whether you approach from the x direction, whether you approach from the y direction, or whatever may be the m value, you select it and try to approach it, you will still reach the same point. Got it? Note it down. Now we see this function. So w is equal to f of z, nothing but u plus iv, or u is a function of x comma y plus I times of v is a function of x comma y. So uv function. Now f of z plus delta z, nothing but for this particular function u became x plus delta x and y plus delta y minus, so again plus I times v x plus delta x plus y plus delta y. So this is the functional change. That means for each variable there will be a minor change, delta x and delta y, right? So then only it will reflect the function value f of z plus delta z. Now you are trying to find out the limit delta z tending to 0. Then f of z plus delta z minus f of z divided by delta z. And this is the limit which we want to find out. So which essentially means that this is limit delta z tending to 0 f of z plus delta z is nothing but u of x plus delta x, y plus delta y minus u of x comma y plus I times v of x plus delta x comma y plus delta y minus v of x comma y. So this is f of z plus delta z minus f of z divided by delta z. So this is the function value which we need to be identifying. Now here delta z tending to 0, we mean delta z is equal to delta x plus delta y, I times delta y. Now this delta x and delta y both are tending to 0 as delta z is tending to 0. Now you can take two different ways. One is delta y tending to 0 first and then delta x tending to 0 next. Or the other way, delta x tending to 0 first and then delta y tending to 0, because you have identified two different variables for the corresponding function f of z plus delta z minus f of z. So you can take either of the case. Now one case, if delta y is equal to 0 and delta x tending to delta z. So this is limit delta x tending to 0, then delta y is equal to 0. So you have made delta y 0 and then you have identified the function value u of x plus delta x comma y minus u of x comma y plus I times of v of x plus delta x comma y minus v of x comma y divided by, as delta y tending to 0, then this you call as delta x. This is the first limit. So the way we have done for the left limit, right? So this is what we have done, delta x tending to 0 and delta y is equal to 0. So this is one case. So there is no change in the value of y, but there is a definite change in the value of x alone. And that means you are trying to approach the value along x direction. Now here, this if you divide, so this u, there is a change in the value of x alone, and this region will become dou u by dou x. And this will become I times dou v by dou x. And this is what we have defined, that is limit delta z tending to 0 f of z plus delta z. We call this as dw by dt. This is condition number 1. Got it or not? You have identified just delta x tending to 0 as delta y being 0. So this is one direction you are trying to approach the value of delta z tending to 0. This is one case. Understood or not? Others, other than Hitesh, anybody else, any questions? Okay, great. Now exactly in the similar manner, what we do is, we take delta x 0 and delta y tending to 0. So limit delta y 0, sorry, delta x 0 and delta z tending to I delta y automatically. Right, I delta y. Then delta y you can tend into 0. That means this is u of x comma y plus delta y minus u of x comma y plus I times of v of x comma y plus delta y minus v of x comma y divided by delta z. I change this as I delta y because delta x is equal to 0, right? Then this is delta y tending to 0. So delta z is equal to I delta y, delta x is equal to 0 and delta y tending to 0. Now if you put it here, this is u of y x comma y plus delta y minus u of x comma y divided by I delta y and delta y tending to 0, which means this is 1 by I times of dou u by dou y plus I times of, this is dou v by I divided by I times of dou v by dou y. So this I cancel, 1 by I means minus I. So this is dw by dz is equal to dou v by dou y minus I times dou u by dou y. This is condition number 2. Got it? Now, as per the fundamental theorem of limit, both the limits should be equal. Then only, this is the minimum required condition. Both the limits should be same. Then only we say that there is a possibility of limit existence. So that's why this is the necessary condition. So necessary condition, the first one, when delta x is equal to turning to 0 and delta y equal to 0, whatever the limit value you have got. And the other way, this is delta x is equal to 0 and delta z tending to I delta y when delta y tending to 0. And this is what we call as the second limit. Both should be equal. As the theorem of complex analysis says that the corresponding terms are equal. That's what we call as the ordered pair. That means the real values are equal and the imaginary values are equal. Which means dou u by dou x is equal to dou v by dou y. This is one condition. And the second condition is dou u by dou y or dou v by dou x is equal to minus dou u by dou y. So these two are called the CR equations or the Cauchy-Riemann equations. These are the fundamental equations. You can note down that. These are the necessary condition is the CR equations. Let me know once you note it down. Done? Noted down? So these are the fundamental equations which we call as the CR equations are must for the derivative to exist. The sufficient condition, we mean the sufficient condition is nothing but the derivative value. So the sufficiency means the derivative should be able to calculate it. That is, if I take that f of z plus delta z, so this value you can express with the help of Taylor's expansion. So this Taylor's expansion, this is so u plus iv, right? So this is u of x comma y plus dou u by dou x times of delta x plus dou u by dou y times of delta y plus higher order terms. You can ignore the higher order terms plus I times v of x comma y plus dou v by dou x to delta x plus dou v by dou y into delta y plus higher order terms, you can ignore it. And then this, if you further simplify it, u of x comma y plus I times v of x comma y plus dou u by dou x into dx plus I times dou v by dou x into dx plus dou u by dou y into delta y plus I times dou v by dou y into delta y. Right? So this is here, this can be expressed as f of z because u plus iv is f of z. Now if I bring it, so f of z plus delta z is equal to f of z plus I times dou u by dou x into dx plus I times dou v by dou x into delta x plus here dou u by dou y can be expressed as minus dou v by dou x into delta y plus dou v by dou x, dou y can be expressed as I times of dou u by dou x into delta y. Here this is f of z plus delta z minus f of z is equal to dou u by dou x plus I times of dou v by dou x times delta x minus here delta y, if you take it out, dou v by dou x plus I times of dou u by dou x. Now this minus I will write as I square, that is plus I if you take it out, and I if you can multiply inside, this is I square. I hope you understood. Minus 1 I have written as I square. So this I square, right? So 1 I kept it here, and then I actually I have brought it inside. How this step? See this, what I have done is very simple. See this value I have written as f of z. Dou u by dou x into delta x, I times dou u by dou x into delta x, I have kept as it is. And this part, dou u by dou y, I have written as minus dou v by dou x, because actually the CR equation states that dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. Got it? These are the CR equations. I have replaced the CR equations here. Then what I have done? I have taken this minus 1 out. That is minus delta y into dou v by dou x minus dou u by dou x. Here minus I have written as I square. So because minus 1 is nothing but I square, 1 I kept it here, 1 I brought it inside. This is I times of dou u by dou x plus I square times of dou u by dou x. Got it? Okay. So then this is dou u by dou x plus I times of dou v by dou x sorry, this is minus here. When you brought this minus 1 outside, this will become minus. So minus of I square will become plus now. I delta y, this is dou u by dou x plus I times of dou v by dou x. So this dou u by dou x plus I times of dou v by dou x into delta x plus I delta y. So this can be replaced with dou u by dou x plus I times of dou v by dou x into delta z. So if you bring this delta z to the other side, this is limit delta z tending to 0, f of z plus delta z minus f of z divided by delta z, and this is equal to dou u by dou x plus I times of dou v by dou x, and this is what we call as the sufficient condition. So this sufficient condition, in short, you can write here dw by dz is equal to dou u by dou x plus I times of dou v by dou x. So this is the sufficient condition for the function to be differentiable. I shouldn't be there. No, it should be there. So I times of dou v by dou x, right? Yeah. Got it? So here dou v by dou z is, or if you apply the CR equations on the same thing, dw by dz is equal to dou u by dou x can be written as dou v by dou y plus I times of dou v by dou x can be written as minus I times of dou u by dou y. You can write either way, both are same. So just replace with the CR conditions, both are one and the same. But in short, you can remember only one like this, and the CR equations here, you need to remember both. So these two are must. So that's why you have to remember both the derivative value and the CR equations. You can note down this. Once you note it down, then we will go and define what is an analytic function. Now this derivative, we tried defining it, right? Now this derivative, right? So it is subjected to a single point. Now suppose if you have identified one region wherein the derivative value, if you wanted to check for the function where w is equal to f of z within the region R, that is, this is the region defined by this entire thing. This is the region what we wanted to identify. Now for this region, whatever may be the point you selected, and then you try to find out the derivative value at that particular point by identifying the necessary points surrounding it. Then we say that the function is differentiable at every point on the region identified by R. So if the function is differentiable at every point within the region identified by the region R, then we say that the function is analytic within R. Suppose if the function derivative doesn't exist one point within the region R, within the region R, then we say that the function is not analytic. It's not analytic at that point. And the point is called the singular point. And the point is called singular point. Got it? So suppose if the function derivative doesn't exist at this point, then this is the point of singularity. And the function is analytic in the entire region R except this point. That means the derivative exists for all the points within this region except this point. This point is a singular point and rest of the region is an analytic region. Got it? So this is only on Z plane. I hope you are aware of it. Because this is what we are talking about is the domain, not about the range. So domain has to be identified only in the Z plane. Got it? So note down this. So there is one more kind of function you can think of, that is, suppose if the function is analytic the entire Z plane. The entire Z plane means whatever may be the value of x and y you can think of, that is my x value from minus infinity to plus infinity and the y varying from minus infinity to plus infinity, that will constitute the entire region of the Z plane. Then we call this function as entire function. Entire function means the derivative exists for the function in the entire region of the Z plane. So for example, any polynomial is an entire function. Polynomial. because for any polynomial, the derivative exists at every point. Got it? So this is one example of entire function. You don't need to confine to a specific region. You can think of the entire region of the z plane for the derivative to exist. Hence, this is an entire function, which essentially means that the function is analytic at every point on the z plane. Clear? So this is the theory that is needed. Understood? Or do you have any questions on this theory? Any questions? Okay. Now actually we will solve some of the problems based on this understanding. If f of z is analytic function, sorry, if w is equal to log z, w is equal to log z, find dw by dz and determine where w is non-analytic. Find dw by dz and determine where w is not analytic. Can you try solving this? Here w is equal to log z. Then w is equal to log of x plus iy or log of x square plus y square under root tan inverse of e power I tan inverse of y by x. This is how you can write it. Any complex number can be expressed as x plus iy can be expressed as r e power I theta, where r is equal to x square plus y square under root and theta is equal to tan inverse of y by x. Any complex number can be expressed in this format. Now the same thing I have done here. Here I have drawn the amplitude here, that is square root of x square plus y square, and the argument here e power I tan inverse of y by x. Now this function can be further subdivided as, that is half log x square plus y square plus I times of tan inverse of y by x. Now this is the w function. Here this is u of x comma y and this is v of x comma y. So this is the u function, this is the v function. Now we have identified the u v values. Now you can apply the Cauchy-Riemann equations on this. So that is, first of all, you can check dou u by dou x is equal to dou v by dou y. Then dou u by dou y is equal to minus of dou v by dou x. Now these two should be satisfied for the derivative to exist first. First you check this. Then if you are done with it, then you can express dw by dz dash dou u by dou x plus I times of dou v by dou x. Calculate this and tell me what is the answer you got it. Yeah. Then tell me what is the derivative value dw by dz in terms of dou u by dou x plus I times of dou v by dou x. What is dou u by dou x? Dou v by dou y also you have to calculate it. Yeah, so Hitesh got correctly. Not plus, actually it is minus. Yeah, yeah, correct, you are correct. So x minus iy divided by x square plus y square. So that's what is the derivative. Now here, if you notice, what we have got is dw by dz is nothing but x minus iy divided by x square plus y square. Now this x square plus y square can be written as x minus iy divided by x minus iy into x plus iy. Got it? So this is equal to x square plus y square. Now this x minus iy and this x minus iy both will cancel out. This will become 1 by x plus iy, which is nothing but 1 by z. So this is dw by dz is equal to 1 by z. Now, in a real function, let y is equal to log x, then it is dy by dx is equal to 1 by x, correct or not? So in a real function, the way we have done the derivative for any analytic function, provided if you know that the function is analytic, then you can do the derivative as if like it is a normal integral, normal derivative. Got it? dw by dz is equal to 1 by z, because we know the function y is equal to log x, the derivative dy by dx is equal to 1 by x. So exactly in the similar manner, the same function actually we have done the derivative here. So this is the derivative exists at every point except for z not equal to 0. From this actually you can identify z not equal to 0. If z is equal to 0, then the derivative value is infinite, which essentially means it is undefined there. So the function is analytic at every point except at z is equal to 0. So z is equal to 0 is a singular point. Got it? Understood or not? Note down one more. F of z is analytic function with constant modulus. Now actually this is an analytic function. That means CR equations are already satisfied. Constant modulus. So that f of z is constant. Is constant. Now what he has given is f of z is equal to u plus iv, and then what he has given is it is u square plus v square is equal to constant. This is what he has given, and this is an analytic function. Based on this, you have to prove that f of z or u plus iv is equal to constant. Can you prove that? Based on that condition, u square plus v square is equal to c, try to prove that f of z is equal to constant. Anybody got it? I'll give you the approach, you can try it. To take the derivative with respect to x, 2u dou u by dou x plus 2v dou v by dou x is equal to 0. That is one condition. And then take the derivative with respect to y, you will get one more condition. And then both try to express with the same terms, dou u by dou x and dou v by dou x, with the help of CR equations. And then manipulate those values to find out f dash of z value, modulus. And from there you try to prove that f of z is equal to constant. This is the approach. I'll give you 2 minutes time more. You solve it, and then afterwards I'll solve it. Anybody got it? Okay. So let me solve this. See this. If you take the derivative of it, this is 2u dou u by dou x plus 2v dou v by dou x equal to 0, or implies u dou u by dou x plus v dou v by dou x equal to 0. This is equation number 1. Similarly, if you take the derivative with respect to y, 2u dou u by dou y plus 2v dou v by dou y equal to 0. Or this is u dou u by dou y plus v dou v by dou y equal to 0. This you can further simplify as dou u by dou y is nothing but, right? So dou u by dou y is minus dou v by dou x plus v times of dou v by dou x can be written as dou u by dou x equal to 0. This is equation number 2. Now, if you square it and add it, so square the first equation and the second equation together and add it together. So this is u square dou u by dou x whole square plus v square so this is u square dou u by dou x whole square plus u square dou v by dou x whole square u square dou u by dou x whole square plus v square dou v by dou x whole square plus 2uv dou u by dou x into dou v by dou x. Then u square dou v by dou x whole square plus v square dou u by dou x whole square minus 2uv dou u by dou x into dou v by dou x. These two will cancel out and then this is equal to 0 and this is u square plus v square dou u by dou x whole square plus dou v by dou x whole square. This is equal to 0. Got it? Good. So this is u square plus v square is equal to c, we know. So if it is c, then the only possibility is dou u by dou x whole square plus dou v by dou x whole square equal to 0. So this is equal to 0. This is nothing but f dash of z modulus whole square. This is equal to 0. Got it? Because f dash of z is equal to dou u by dou x plus I times of dou v by dou x. Now the modulus of it is dou u by dou x whole square plus dou v by dou x whole square. Now under root. So if you square it, it will be equal to 0. That means the modulus of f dash of z is equal to 0. Hence f dash of z is equal to 0. And then if you take integration on either sides, f of z is equal to constant. This is what he asked us to prove. Got it? Any questions on this? Any questions on this? Yeah, great. So these are some of the models based on finding out the derivative. Now the other cases are the case of failures. Now I am going to give you one problem. You can try it on your own. So that the function f of z is equal to square root of mod of xy is not analytic at the origin, is not analytic at the origin, even though CR equations are satisfied. At origin. Can you solve this? So you take this as homework and then try to solve it. Tomorrow I am going to solve this class. So I am going to solve this problem. Along with that, this kind of models are very crucial. I am going to solve 2-3 more on this. Got it? So you take this as homework and try to solve on your own. So any questions on this? Any questions on this? Got it? Okay. So I'd like to close the class for today. So thank you. Good night. Because actually if I try to solve it, it will be in the middle of the class. Automatically it will end. So thank you. Good night. Bye bye.